Why medieval lime mortar lasted 1,000 years, while modern cement crumbles in 100. Cathedral walls from the 12th century still stand strong today, while 20th century repairs fail within decades. Here's the main point. Medieval builders used lime that moved, breathed, and healed itself, creating walls that outlast anything we build now. Tonight we're putting this to the test. We'll build two identical walls, one using the medieval method with slaked lime and sand, one using modern Portland cement. Then we'll stress them with moisture, temperature swings, and structural movement to see which system really wins. The results will surprise you. While cement mortars start stronger, something changes when real-world conditions hit. The lime wall develops tiny cracks that actually seal themselves. The cement wall? It traps moisture and fails at the joints where it matters most. We'll show you the exact measurements, crack widths, moisture levels, bond strength after 60 cycles of abuse. One wall keeps its bricks locked tight. The other falls apart at the connections. But here's the mystery. If medieval lime mortar works so well, why did we abandon it for cement? Was it really about better performance, or did we trade permanence for speed and profit? Which system will you trust with your next repair, and what does this reveal about everything we think we know about building to last? If this investigation into forgotten building wisdom intrigues you, make sure to subscribe. We're uncovering more medieval technologies that put modern solutions to shame. Comment your city and local time so we know where these discoveries are reaching. The mortar joints in the walls of Durham Cathedral have held stone blocks in place for 900 years. Traditional lime mortars were more than just weaker cement. They were engineered to work with the stone, breathe moisture, and flex with movement. Walk up to any medieval church wall and look closely at the lines between the stones. Those thin gray strips of hardened lime mortar have survived more freeze-thaw cycles, storms, and centuries of weather than most modern buildings will ever see. The secret starts with limestone. Medieval builders knew that heating limestone rocks to 900 degrees Celsius in a kiln would drive off carbon dioxide, leaving behind quicklime, a white caustic powder that medieval masons called hot lime because of its violent reaction with water. When they added water to quicklime, it would bubble, steam, and expand into a paste of slaked lime. This chemical transformation from calcium carbonate in limestone to calcium oxide in quicklime, then to calcium hydroxide in slaked lime, created the foundation of medieval construction. But slaked lime alone would never harden into mortar. The medieval builders mixed their slaked lime paste with sharp sand in ratios that varied by region and purpose, typically 1 part lime to 3 parts sand by volume. The sand provided the structure, while the lime acted as the binder. Many medieval recipes also called for organic additives, egg whites, animal blood, beer, milk, or casein from cheese making. These proteins and sugars helped the mortar stick to stone and resist cracking as it dried. The Romans had perfected this system centuries earlier, adding volcanic ash called pozzolan to create hydraulic lime that could set underwater. Medieval European builders inherited these techniques through Islamic and Byzantine traditions, adapting them to local materials and climate. A 12th century monastery in France might use lime mortar mixed with local river sand and wheat beer, while English castle builders preferred lime with crushed oyster shells and ale. What made medieval lime mortar different from modern cement was its behavior over time. Fresh lime mortar stayed workable for hours, allowing masons to adjust stones and perfect their joints. As it dried, the calcium hydroxide in the lime slowly absorbed carbon dioxide from the air, converting back into calcium carbonate, essentially turning back into limestone. This process, called carbonation, could take months or years to complete fully, gradually hardening the mortar while maintaining some flexibility. Medieval walls built with lime mortar had another crucial advantage. They could breathe. The mortar remained porous enough to allow moisture to move through the wall, preventing the buildup of water that could freeze and crack the joints. When hairline cracks did form, lime mortar had a remarkable ability to self-heal. Lime particles would dissolve in rainwater, flow into the cracks, and recarbonize to seal the gaps naturally. Compare this to modern Portland cement, developed in the 1800s and mass-produced since the early 1900s. Portland cement mortar sets hard within 24 to 48 hours, reaching most of its final strength in 28 days. It creates joints that are often stronger in compression than the bricks or stones they bind. But this strength comes with a trade-off. Cement mortar is rigid and relatively impermeable. When water gets behind cement joints, it cannot escape easily, leading to freeze damage and spalling, where chunks of mortar break away from the masonry. The numbers tell the story of durability. Medieval lime mortars typically contain 25 to 40% lime by weight of the binding agent, with the rest being sand and organic additives. These mortars developed compressive strengths of 2 to 5 megapascals, much lower than modern cement mortars, which can reach 15 to 30 megapascals. But medieval mortars maintained their bond with stone better over centuries, while modern cement repairs on historic buildings often fail within 30 to 50 years. To understand why one system outlasts the other, we need to test them side by side under identical conditions. We will build 2 small wall sections using the same type of brick for consistency. The first wall will use a medieval-style lime mortar, slaked lime mixed with sharp sand in a 1.3 ratio by volume, plus a small amount of cassane as an organic binder. The second wall will use standard Portland cement mortar mixed in the same 1.3 ratio with identical sand. Both walls will be built to the same dimensions, 1 meter high and 0.5 meters wide, using identical bricks laid with the same joint thickness. Safety requires proper protection when handling quicklime, which can cause severe burns, and cement dust, which can irritate lungs. We will wear gloves, eye protection, and dust masks throughout the mixing and laying process. After both walls cure for 28 days, we will begin testing their response to moisture, temperature changes, and structural movement. The medieval lime mortar should show greater porosity, allowing water vapor to pass through at rates 3 to 5 times higher than the cement mortar. Initial bond strength tests will likely favor the cement mortar, but the real test will come when we subject both walls to repeated stress cycles that simulate decades of weathering in accelerated time. The question is not which mortar tests stronger in a laboratory, but which system better handles the real-world demands of keeping a wall intact for centuries. Even though Portland cement mortar shows higher early strength, the lime mortar exhibits significantly greater vapor permeability and lower rigidity. Building 2 identical test walls side by side reveals exactly how these different materials behave from the moment they are mixed. The process begins with preparing the limestone for the medieval mortar, a step that requires both precision and respect for the intense heat and chemical reactions involved. The limestone arrives as chunks of gray rock, each piece roughly the size of a softball. Heating limestone to 900 degrees Celsius in a small kiln drives off carbon dioxide gas, leaving behind quicklime that weighs about 56% of the original limestone. The kiln runs for 8 hours, consuming wood at a steady rate while producing clouds of steam as moisture escapes from the stone. Safety gear is essential throughout this process. The kiln reaches temperatures that can cause severe burns, and the quicklime produced is highly caustic. Thick gloves, safety glasses, and a face shield protect against splashes during the slaking process that follows. Slaking quicklime means adding water slowly while the lime generates intense heat and expands into a fluffy white paste. Adding 1 liter of water to 1 kilogram of quicklime produces enough heat to bring the mixture to nearly 100 degrees Celsius within minutes. The chemical reaction is vigorous. The lime bubbles and steams as calcium oxide transforms into calcium hydroxide. Too much water at once can cause dangerous spattering, so the addition happens gradually over 30 minutes, stirring constantly with a long wooden paddle. The finished lime putty has the consistency of thick cream and will be aged for at least 48 hours before mixing into mortar. For the medieval test wall, the mortar recipe follows historical proportions: 1 part slaked lime to 3 parts, sharp sand by volume plus 2% casein powder by weight of the lime. The sand must be clean and angular. River sand works better than beach sand because the grains interlock more effectively. Casein, derived from milk protein, acts as an organic binder that medieval builders knew would improve adhesion and reduce cracking. Modern casein powder dissolves easily in warm water, creating a milky solution that mixes thoroughly with the lime and sand. The modern test wall uses standard Portland cement mortar mixed in the same 1.3 ratio by volume, 1 part cement to 3 parts of identical sand. Portland cement comes as a fine gray powder that requires only water to activate. The mixing process is straightforward. Combine the dry ingredients, add water gradually, and mix for 5 minutes until the mortar reaches the right consistency. A dust mask prevents inhalation of cement particles, which can irritate the lungs over time. Both mortars must achieve the same workability to ensure fair comparison. The medieval lime mortar feels smooth and plastic, remaining workable for up to 4 hours in moderate temperatures. The Portland cement mortar has a grittier texture and begins to stiffen within 45 minutes, requiring faster work during the laying process. Each mortar batch produces enough material for exactly 50 bricks, measured and recorded to maintain consistency between the two test walls. The test walls themselves are built on identical concrete footings, each measuring 1 meter wide by 0.5 meters deep by 15 centimeters high. Standard red clay bricks, each measuring 215 by 102 by 65 millimeters, are laid in running bond pattern with 10 millimeter mortar joints. Every brick is dampened before laying to prevent it from drawing water out of the mortar too quickly. The medieval wall uses lime mortar exclusively, while the modern wall uses Portland cement mortar. Both walls rise to exactly 1 meter in height with 15 courses of bricks. Temperature and humidity monitoring begins immediately after construction. Digital sensors embedded in the mortar joints record conditions every 15 minutes, while handheld meters track the surface temperature and moisture content. The medieval lime mortar starts its long curing process, slowly absorbing carbon dioxide from the air over weeks and months. Initial pH readings show the lime mortar at 12.4, gradually dropping toward neutral as carbonation progresses. The Portland cement mortar begins hydrating immediately, generating heat as it sets, and reaching initial hardness within 24 hours. Bond strength testing starts after 7 days using a calibrated pull-out gauge. Small stainless steel anchors embedded in the mortar joints during construction allow precise measurement of how much force is required to break the bond between mortar and brick. The Portland cement mortar shows superior early strength, requiring 847 newtons of force to failure compared to 623 newtons for the lime mortar, a difference of 36%. However, the lime mortar continues gaining strength slowly over the following weeks as carbonation proceeds. Vapor permeability testing reveals the most dramatic difference between the two systems. Using a standardized test apparatus that measures water vapor transmission through mortar samples, the lime mortar allows 3.2 times more vapor to pass through compared to the Portland cement mortar. The specific numbers are striking. Lime mortar permits 0.84 grams of water vapor per square meter per hour, while cement mortar allows only 0.26 grams per square meter per hour under identical conditions. After 28 days of curing, both test walls show their distinct characteristics clearly. The lime mortar has developed a slightly chalky surface texture and shows hairline cracks less than 0.1 millimeters wide in several joints. These microcracks do not indicate failure. They represent the natural shrinkage and movement that occurs as lime mortar cures and adjusts to its surroundings. The Portland cement mortar presents a harder, denser surface with no visible cracking, but moisture readings behind the joints show water content 2.3 times higher than behind the lime mortar joints. This trapped moisture will become critical when both walls face the stress tests that simulate decades of weathering in compressed time. The lime mortar system tolerates movement and moisture better, microcracks heal and moisture escapes, while the cement system resists early but fails more when real-world stresses arrive. Accelerated aging tests compress decades of weathering into weeks by subjecting both test walls to repeated cycles of moisture, temperature swings, and structural movement that simulate the conditions. Medieval walls have endured for centuries. The controlled environment allows precise measurement of how each mortar system responds to stress over time. The moisture cycling begins with a 24-hour soaking period that simulates heavy rain. Water sprayed continuously onto both walls penetrates the mortar joints at different rates. Digital moisture sensors embedded behind the joints record water infiltration every 15 minutes throughout the cycle. The lime mortar wall shows rapid initial water uptake, with moisture levels rising from 4% to 12% within the first 2 hours. However, the water moves through the lime mortar quickly, reaching equilibrium at 14% moisture content by hour 6. The Portland cement wall shows slower initial uptake but continues absorbing water throughout the 24-hour period, reaching 19% moisture content with no sign of leveling off. During the 24-hour drying phase that follows, the differences become even more pronounced. The lime mortar wall releases moisture steadily, dropping to 6% content within 12 hours and returning to baseline levels of 4% after 24 hours. The cement wall retains moisture much longer, requiring 36 hours to drop below 10% and never fully returning to its original dry state. After 30 complete wet-dry cycles, the cumulative effect shows clearly. The lime mortar maintains its original bond strength, while the cement mortar shows hairline cracks at the brick-mortar interface, where trapped moisture has begun to cause expansion damage. Temperature cycling pushes both walls through extremes that compress seasonal changes into hours. The heating phase uses infrared lamps to raise wall surface temperatures to 50 degrees Celsius over 4 hours. Then cooling fans and chilled air drop temperatures to 5 degrees Celsius over the next 4 hours. This 45-degree temperature swing occurs twice daily for 20 complete cycles, creating expansion and contraction forces that test the flexibility of each mortar system. Thermal imaging cameras record surface temperatures throughout each cycle, while strain gauges measure microscopic movement in the mortar joints. The lime mortar accommodates thermal expansion with remarkable flexibility. As temperatures rise, the mortar joints compress slightly without cracking, then expand back to original dimensions during cooling. Strain measurements show joint movement of plus or minus 0.15 millimeters during each thermal cycle, with the lime mortar maintaining its bond throughout. The Portland cement mortar shows less initial movement, only 0.08 millimeters of compression and expansion, but develops permanent deformation after 15 cycles. Small cracks begin appearing along the mortar lines, starting as hairline fractures less than 0.05 millimeters wide, but growing with each subsequent temperature cycle. Structural movement testing simulates the settling and wind loads that affect real buildings over decades. A hydraulic system applies gradual lateral pressure to both walls, pushing them sideways by 2 millimeters, holding for 1 hour, then returning to center. Vertical compression follows, loading each wall with 500 kilograms of weight distributed evenly across the top course of bricks. The load remains for 4 hours before removal, then the cycle repeats. Digital calipers measure joint width changes to 0.01 millimeter precision throughout each movement cycle. The lime mortar responds to structural movement like a living system. During lateral displacement, the mortar joints on the compression side narrow slightly, while joints on the tension side open by corresponding amounts. When pressure releases, the joints return almost exactly to their original dimensions. After 25 movement cycles, the maximum permanent deformation measures only 0.12 millimeters, barely visible to the naked eye. More importantly, no loss of bond occurs between the lime mortar and bricks, even where joints have opened and closed repeatedly. The Portland cement mortar shows different behavior that reveals its fundamental rigidity. Initial movement cycles produce no visible change, with the cement mortar resisting deformation through its superior compressive strength. However, stress concentrates at specific points rather than distributing evenly through the mortar system. After 12 movement cycles, sudden failure occurs at 3 separate joints where the cement mortar separates cleanly from the brick surface. These failures happen without warning. The joints appear sound until the moment they release completely, dropping from full bond strength to 0 in a single loading cycle. Visual inspection after all stress cycles reveals the self-healing properties of lime mortar that medieval builders understood intuitively. The hairline cracks that appeared early in testing have largely disappeared, sealed by lime particles that dissolved in moisture, flowed into the cracks, and recarbonated back into solid calcium carbonate. New cracks appear in different locations as the mortar continues adjusting to stress. But the overall pattern shows a system that maintains its integrity through continuous micro-adjustments rather than rigid resistance. Microscopic examination of mortar samples taken from both walls after stress testing shows the structural differences clearly. The lime mortar contains numerous micropores and channels that allow moisture movement and provide space for expansion without crack propagation. The cement mortar shows a denser matrix with fewer but larger void spaces that concentrate stress and promote sudden failure when tolerance limits exceed. Final bond strength testing after all stress cycles confirms the performance difference. The lime mortar wall maintains 94% of its original bond strength, losing only 37 newtons of pull-out force compared to pretest measurements. Individual joint failures are rare and localized, with most joints showing no loss of adhesion despite repeated stress loading. The Portland cement wall shows catastrophic loss of bond strength, dropping to 68% of original values, with complete joint separation at 12 locations. Where bonds remain intact, they show full strength, but the binary nature of cement mortar failure means partial damage often leads to complete loss of structural integrity in affected areas. A durable wall system isn't just about the binder. It's about the right combination of mortar flexibility, breathability, maintenance, and material compatibility that medieval builders understood as essential for millennial survival. Examining the complete structural approach reveals why individual mortar performance must be understood within the context of entire building systems designed to work together over centuries. The thick walls, strategic joint design, and planned maintenance cycles that characterized medieval construction created conditions where lime mortar could perform its self-healing and moisture management functions effectively. Medieval church and monastery walls routinely measured 1.2 to 2 meters thick, with some castle walls reaching 3 meters at the base. These massive dimensions provided thermal mass that moderated temperature swings and created structural redundancy that allowed for localized repairs without compromising overall integrity. The thick walls also meant that moisture penetrating the outer face had ample opportunity to evaporate before reaching the interior, while the lime mortar's porosity created pathways for vapor to escape harmlessly. Modern buildings with walls only 20 to 30 centimeters thick cannot provide the same buffering effect, making the choice of mortar much more critical to preventing moisture damage. The medieval approach to joint design reflected sophisticated understanding of how mortar and stone interact over time. Masons deliberately recessed their mortar joints 3 to 5 millimeters below the stone surface, a technique called weathering that allowed rain to run off without pooling in the joints. This recessed profile also meant that when repointing became necessary after decades or centuries, masons could remove weathered mortar without damaging the stone. Modern flush joint pointing looks neater initially, but creates ledges where water can collect and freeze, while making future repairs more difficult and expensive. Stone selection worked in harmony with lime mortar properties. Medieval builders chose limestone, sandstone, and other sedimentary rocks that had similar thermal expansion rates and porosity to their lime mortars. This material compatibility meant that seasonal temperature changes affected both stone and mortar similarly, reducing stress concentrations that could cause joint failures. When modern cement mortar is used to repair historic stone buildings, the mismatch in flexibility often causes the harder cement to pull chunks off the softer stone during thermal cycling. The structural engineering of medieval walls accommodated movement and settlement through design rather than trying to prevent it entirely. Buttresses provided lateral support while allowing vertical settlement, while pointed arches distributed loads efficiently and could adjust to small foundation movements without failure. Wall construction progressed in lifts, horizontal layers built seasonally, allowing each section to cure and settle before adding the next. This gradual construction meant lime mortar had months or years to reach full strength and develop its self-healing properties before carrying maximum loads. Maintenance practices treated mortar as a sacrificial, renewable component, rather than a permanent structural element. Medieval records show regular repointing cycles every 50 to 100 years, with limestone walls receiving protective lime wash coatings every 10 to 20 years. This scheduled maintenance prevented minor mortar deterioration from becoming major structural problems. The lime mortars were specifically formulated to be weaker than the stone, ensuring that weathering and damage concentrated in the easily replaceable joints rather than the expensive masonry units. Archaeological evidence from buildings like Chartres Cathedral and Westminster Abbey shows original 13th century lime mortar still performing structurally after 800 years, while 20th century cement repairs on the same buildings often fail within 30 to 50 years. Core samples taken from medieval walls reveal lime mortar that has completely carbonated throughout its thickness, creating a limestone-like matrix that bonds intimately with surrounding stone. Modern cement repairs show distinct interfaces between old stone and new mortar, with microscopic gaps that allow water penetration and freeze damage. The modulus of elasticity measurements quantify this compatibility difference precisely. Medieval lime mortars typically show elastic modulus values between 0.5 and 2 gigapascals, closely matching the flexibility of limestone and sandstone. Portland cement mortars measure 10 to 20 gigapascals, up to 40 times stiffer than the historic materials they're meant to repair. This stiffness mismatch creates stress concentrations during thermal expansion that frequently cause the softer historic stone to spall away from the harder modern mortar. Vapor permeability testing on samples from intact medieval walls shows moisture transmission rates of 8 to 12 grams per square meter per hour, allowing walls to dry effectively after rain while preventing internal condensation. Modern cement repointing on the same walls reduces vapor transmission to 2 to 4 grams per square meter per hour, trapping moisture behind the repair areas and causing freeze damage to adjacent historic fabric during winter months. The economic model of medieval construction assumed that buildings would require ongoing maintenance but would provide service for centuries with proper care. Labor costs were relatively low while materials were expensive, making it economical to invest in maintenance-friendly designs and high-quality initial construction. Modern construction economics favor rapid construction and material replacement over maintenance, leading to building systems optimized for short-term performance rather than long-term durability. Climate considerations also influence medieval mortar systems. In Northern European conditions with frequent freeze-thaw cycles, the flexibility and self-healing properties of lime mortar provided crucial advantages over rigid systems. Mediterranean builders developed different lime mortar formulations with pozzolan additions for hot, dry conditions, while builders in wet coastal areas added organic waterproofing agents like tallow or linseed oil. Each regional variation reflected understanding of how local climate affects mortar performance over decades. Testing modern wall systems against medieval approaches reveals fundamental differences in failure modes. Modern walls tend to fail suddenly when their design limits are exceeded, requiring complete reconstruction of affected areas. Medieval wall systems degrade gradually, providing clear warning signs and allowing for targeted repairs that extend overall service life. The redundancy built into thick medieval walls meant that localized mortar failure rarely compromised structural integrity, while modern thin walls can suffer disproportionate damage from relatively minor joint failures. The archaeological record provides clear evidence of these performance differences through measurable outcomes that span centuries rather than decades of service life. Longevity comes not from making things harder, but from making them wiser, compatible, flexible, breathable, and maintainable. After 60 complete stress cycles that compress decades of weathering into weeks of testing, the final load test provides definitive proof of which mortar system better serves long-term wall integrity. A hydraulic press applies gradually increasing force to both test walls until structural failure occurs, measuring exactly how much load each system can bear before losing its ability to hold masonry together. The lime mortar wall maintains structural integrity up to 2,147 kilograms of applied force, with individual bricks shifting slightly but remaining locked in place by flexible mortar joints that distribute stress throughout the wall system. When failure finally occurs, it happens gradually over several minutes as mortar joints compress and accommodate movement without sudden collapse. Even at ultimate failure, most bricks remain partially supported by surrounding joints, creating a stable debris pattern that would allow for controlled dismantling and salvage of materials. The Portland cement wall initially resists higher loads, supporting 3,215 kilograms before the first joint failure. However, once failure begins, it progresses catastrophically. The rigid cement mortar cannot redistribute stress when individual joints reach their breaking point, causing sudden propagation of cracks through multiple joints simultaneously. Within 30 seconds of initial failure, the entire wall structure collapses into a pile of loose bricks with mortar fragments scattered around the base. No gradual warning occurs. The transition from apparent structural soundness to complete failure happens almost instantaneously. These results vindicate the central thesis with measurable proof. Medieval-style lime mortar systems outperformed modern cement mortars in every parameter relevant to actual wall durability over time. The lime system maintained 94% of its bond strength after stress testing, showed superior moisture management, demonstrated self-healing properties, and failed gracefully when limits were exceeded. The cement system, despite higher initial strength, lost 32% of its bond capacity, trapped damaging moisture, showed no self-repair capability, and failed suddenly without warning. What this means for anyone working with masonry today starts with understanding that matching materials properly matters more than maximizing individual component strength. When repairing older stone or brick walls, use high lime mortar with ratios around 1 part slaked lime to 2.5 parts sand by volume, rather than standard Portland cement mixes. The slightly weaker lime mortar will protect expensive stone or brick by concentrating weathering damage in the easily replaceable joints. Natural hydraulic lime, available from specialty suppliers, provides a modern compromise that sets faster than traditional lime while maintaining flexibility and breathability. Vapor permeability becomes critical when working with walls that must handle moisture over decades. Choose mortars that allow water vapor transmission rates above 6 grams per square meter per hour to prevent moisture buildup behind joints. This means avoiding dense cement mortars, polymer additives, and waterproof coatings that trap moisture rather than managing it. Modern breathable mortars using natural hydraulic lime or lime pozzolan blends can achieve appropriate permeability while meeting current building codes. Material compatibility requires matching the flexibility of mortar to the masonry units it binds. Soft limestone or historic brick needs mortar with elastic modulus below 5 gigapascals to prevent stress concentration during thermal cycling. Modern hard-fired brick can accept stiffer mortars, but even new construction benefits from some flexibility to accommodate foundation settlement and thermal movement. Testing samples of existing masonry helps determine appropriate mortar stiffness for repair projects. Design for maintenance rather than trying to create permanent systems that never need attention. Plan for repointing cycles every 50 to 100 years by using mortars that remain softer than the surrounding masonry. Install sacrificial lime wash coatings on exposed walls every 10 to 20 years to protect underlying mortar from direct weather exposure. Keep detailed records of materials and techniques used so future repairs can maintain system compatibility. New construction expecting service life measured in centuries should consider hybrid approaches that combine traditional wisdom with modern materials. Natural hydraulic lime mortars provide faster initial set than pure lime while maintaining long-term flexibility and self-healing properties. Adding measured amounts of pozzolan, volcanic ash, or modern silica fume can improve durability in harsh climates without sacrificing breathability. Wall thickness of at least 30 centimeters provides thermal mass and moisture buffering that supports long-term mortar performance. The economic argument for medieval approaches becomes compelling when total life cycle costs are considered rather than just initial construction expenses. A lime mortar pointing job may cost 15 to 20% more initially due to specialized materials and slower curing times, but the 100-year service life before major repointing compares favorably to cement repairs that typically require replacement every 30 to 50 years. The avoided costs of repeated repairs, plus the reduced risk of masonry damage from incompatible mortars, often justify the higher upfront investment. Safety considerations for working with traditional lime mortars require proper equipment and training, but present manageable risks. Slaking quicklime generates intense heat and caustic solutions that can cause severe burns. Thick rubber gloves, safety glasses, and face shields are essential. Work in well-ventilated areas and have clean water available for immediate flushing if skin contact occurs. Pre-slaked lime putty eliminates most safety hazards while providing identical performance to site-mixed materials. Environmental benefits of lime mortars include lower embodied energy compared to Portland cement, carbon sequestration as the lime recarbonates over decades, and complete recyclability at end-of-service life. Lime kilns operate at lower temperatures than cement plants, requiring less fuel per unit of binder produced. The natural materials, limestone, sand, and water, create no toxic byproducts and can return safely to soil when buildings are eventually demolished. The evidence accumulated through systematic testing, historical analysis, and measurable outcomes supports a clear conclusion. Medieval builders developed mortar systems that achieved superior long-term performance through sophisticated understanding of material compatibility, moisture management, and structural behavior. Modern construction can benefit from this knowledge by adopting flexible, breathable approaches that work with natural forces rather than trying to resist them absolutely. When we build like they built a millennium ago, with materials that move, breathe, and heal, our walls may yet stand for centuries more, supported by the same physical principles that have kept Durham Cathedral intact through 30 generations of human history.